Welcome to Homework Lib.
So in this question, we have a hypothetical molecule. So it doesn't necessarily exist. We have nitrogen and hydrogen, and we try to bond them together. So we want them to make a rotational level transition from L equals 3 to L equals 1, and it gives off a photon of wavelength 1.78 nanometer when it transits. So we want to work out what is the separation between the two atoms in this molecule. What is the separation? And we know that the mass of hydrogen, mH, is 1.67 times 10 to the negative 27 kilogram, and the mass of nitrogen is 2.33 times 10 to the negative 26 kilogram. So given that, we would like to know the distance between them. So in order to do that, we have to again use our energy formula. The energy for each level is L times L plus 1, h squared over 2I. So the energy transition from L equals 3 to L equals 1, delta E, is when L equals 3, it's 3 times 4. 3 times 4, when L equals 1 is 1 minus 2. H squared over 2I. So this is equal to 3 times 4 is 12. 12 minus 2 is 10. And then, so it is 5 times h squared over I. The 2 cancels. And then, since delta E also equals to hc over lambda, we can establish this equation that hc over lambda equals 5 times h squared over I. So from this, we are able to find out what I is. So solving I gives I equals 5 times I equals over C lambda is 5h lambda over C. Okay, and so if we calculate this, in the book, it's more often that we use h bar instead of h. So we can also use 5 times h bar is 1.055 times 10 to the negative 34 joules second over 2 pi times 1.780 nanometer. C is 3 times 10 to the 8 meter per second. So this is 4.981 times 10 to the negative 52 kilogram meter square. And then we know that I equals the reduced mass times R naught squared. So we can find the separation R naught if we do R naught squared equals R naught squared equals I over R, MR, but then so R naught equals I over MR square root. And then the reduced mass is equal to mass of nitrogen times mass of hydrogen over mass of nitrogen plus mass of hydrogen. Okay, so now if we start to, this is one, put in everything, we will get 4.981 times 10 to the negative 52 over 1.67 times 10 to the negative 27 times 2.33 times 10 to the negative 26. And then here we have them plus together, 1.67 times 10 to the negative 27 plus 2.33 times 10 to the negative 26. Okay, and if we calculate them, we will get that this equals 5.65 times 10 to the negative 13 meter. So if you actually compare this to a normal molecule, you'll see that this separation is much, much smaller than the diameter of a typical atom. So this is not very realistic, so this hypothetical molecule actually shouldn't exist.